I'm Felix, and recently I've been looking at this. Oh God, oh, not that. I mean, I've been looking at this.
Heisenberg is largely thought of as the founder of quantum physics. He came up with the uncertainty principle, which is now one of the most famous equations of all time. This version here is called the position-momentum uncertainty equation, but I'll come back to that in a little bit, because we want to know a little bit more about what uncertainty is. Uncertainty is a measure of how sure we can be that a measurement we take really is the true value. If I try to measure the length of a line, but I'm wearing a stupid fursuit and shaking the ruler, then I'm probably going to be off by a few centimeters or inches for our overseas buddies. Let's say I measure 20 beans, plus or minus 1 bean. That means I can be 68% sure that I have somewhere between 19 and 21 beans. I'm not too sure why I'm uncertain about my beans. And to be honest, all I ever want is more beans. And all this talk about beans is making me rather upset. Anyway, the 68% is convention that all uncertainties are quoted to. It's associated with the probability of being within one standard deviation of the mean on a normal distribution. This triangle is called delta, and the thing in front of it is what we're uncertain of. Okay, now back to the equation. You can see that this equation deals with the uncertainty of x and the uncertainty of p. X is the position of the thing that we're measuring, and p is the momentum. Momentum is directly proportional to velocity, which tells us about where the thing is going. The equation tells us that multiplying these two uncertainties together must always be greater than or equal to this term here. This term turns out to be really small, which is why we have to get down to a quantum level to see these kind of things going on. H bar is a hugely important number in quantum physics. It pops up everywhere, like in the Schrödinger equation, or relating the wavelength of light to its energy. Let's say we measure the position of a particle super well by forcing it through a thin slit. You can think of this like a globe. If the hole is small, then you know where it's going to be. The uncertainty in the position is really small. In fact, it's so small that it starts to violate the equation. Delta P must increase to keep everything in balance, which now means we're more uncertain about where it's going. You can see this in a great demonstration by Veritasium. So the uncertainty principle means we can either know where something is or where it's going, but not both simultaneously, or at least not to any great accuracy. That's the overall message. But I'd really like to look at this from a more quantum physics-based perspective. So if you'll bear with me for a few more minutes, I'm sure you'll have a much better understanding. But for the next few moments, please relax to these images of ferrets side by side with mountains. In quantum physics, everything we want to know about a system is contained within this thing called the wave function. It's kind of like a mathematical description of the system. Every time we want to find out something about the system, we use these things called operators to extract the information we want from the wave function. The operator tells us the expected value we'd get if we actually did a measurement. There's operators for everything. Position, momentum, energy, beans? Well, maybe not beans, but I'm sure we could look into it. The hat means that it's an operator. If we want to know two things about a system, then we just use two operators. But that gives us a choice of order. Doing x then p is like saying measure the position, then measure the momentum. And if doing x then p is different to p then x, then measuring one changes the value of the other, since their outcomes are different. If we do x times p minus p times x and it's 0, then we know there's no difference between the order that we measure things. But if it's not 0, then it matters. We can actually pop the non-zero term into the generalized uncertainty equation, and out pops Heisenberg's uncertainty principle. We can actually do this for any measurables, like energy and time. And this actually leads to the same thing. This actually leads to some mind-blowing conclusions. Like, since we're uncertain about the energy of a system, we can actually violate conservation of energy. We can create and destroy energy as long as it's for a short amount of time. This leads to the extraordinary phenomenon of virtual particles, and I'd love to talk about that in a future video. Either way, I hope you got something good out of this video, and let me know what I can improve on. Until next time.